Hello everyone, I'm Rémi Vatrigan from Lyon in France, and this is a talk of our paper on algorithmic weakening of the Erde-Hajnal conjecture. So this is joint work with my colleagues from Lyon, Edouard Bonnet, Stéphane Thomasé, and Tang Tran. So this paper deals with the Erdos-Hajnal conjecture, and the Erdos-Hajnal conjecture deals with the concept of H-free graphs. So H-free graphs are graphs with a forbidden pattern H that we forbid as an induced subgraph. So for instance, P3 free graph, we forbid the path of size with 3 vertices as an induced subgraph. So there's a constraint on the edges, but also on the non-edges. So for instance, this graph is not P3 free because there are several P3s. So for instance, this one in red. But if we delete this edge, then we get a P3 free graph. We cannot find an induced subgraph that is isomorphic to P3. The second idea in the Erdos-Hajnal conjecture is about homogeneous sets, and a homogeneous set in a graph is either a clique or an independent set. A clique being a set of pairwise adjacent set of vertices, and an independent set being a set of pairwise non-adjacent set of vertices. So the Erde-Hajnal conjecture says the following: any graph H satisfies the Erde-Hajnal property, and the Erde-Hajnal property is the following. There's a constant epsilon, which depends on H, such that any H-free graph on n vertices must contain a homogeneous set of size n to the power of this constant epsilon. So it either has a clique of size this size, or an independent set of this size. So just to take some easy observations, observe that in random graphs, the expected size of a homogeneous set is roughly log n. So the Erde-Hajnal conjecture says that whenever you forbid some fixed graph H in your graph, then the size of a homogeneous set must increase from log n to some polynomial in n. Unfortunately, not so many graphs H are known to satisfy this Erde-Hajnal property. We can mention the case of P3 free graphs that we have talked about previously. So actually P3 free graphs are disjoint union of cliques. So it always have either a clique of size square root of n, or this is a disjoint union of square root of n cliques. In that case, there is an independent set of size square root of n. So there is always a homogeneous set of size square root of n. The constant here is 1/2. P4 free graphs, they are also known as cographs, and it is known that cographs are a subset of perfect graphs, and it can easily be seen that perfect graphs satisfy the Erde-Hajnal property, still with the constant 1/2. There is always a homogeneous set of size square root of n in a perfect graph. Another different graph, if you forbid a clique of size r, a fixed clique of size r, then by Ramsey's theorem you can easily prove that there is always an independent set of size at least n to the power of 1/r minus 1 by a simple inductive argument. So you can check that triangle free graphs, they always have a homogeneous set of size square root of n, an independent set in that case of size square root of n in triangle free graphs. Then there are somehow isolated results concerning the bool, which is this following graph, which satisfy the Erde-Hajnal property. It's a result by Chodnowski and Safra. In that case, the constant is 1/4 for the bool. And lastly, it is also known that the Erde-Hajnal property is preserved by the substitution operation. The substitutional operation is the following: if you take two graphs, like for instance this path on 4 vertices and this path on 3 vertices, and you pick one special vertex in the first graph and you replace this vertex by the whole second graph, then you get this graph. And Alan Patch and Solimosi proved that if the two first graphs satisfy the Erde-Hajnal property, then the substitution graph also satisfies the Erde-Hajnal property. So by using these graphs and this substitution operation, you can construct many graphs satisfying this Erde-Hajnal property, but still not that many graphs. So there are very simple graphs which are still open for the Erde-Hajnal property, and the most famous one are P5, the path with 5 vertices, and C5, the cycle on 5 vertices. So it is still open whether Erde-Hajnal hold for these graphs, and this is quite a long-standing open problem in the area. So the Erde-Hajnal conjecture suggests that the structure of homogeneous sets drastically changes in H3 graphs. So a natural question is, are problems drastically easier in H3 graphs, and in particular problems related to the finding of homogeneous sets? So for instance, finding a largest independent set. So alpha of G denotes the size of a largest independent set. So let me recall that in general graph, finding a largest independent set is NP hard not only to solve but also to approximate within any non-trivial approximation ratio, namely within any n to the power of 1 minus epsilon for any epsilon positive. So this is a computationally very hard problem, a very hard optimization problem. In H3 graphs, it is not that easier actually from the approximation point of view. At least it is not trivially approximable. It is still hard. By combining some known reduction, we have the following result for any fixed connected graph H, which is neither a path nor a subdivision of the claw being this small star. Maximum independent set is APX hard in H3 graphs. APX hard means that there is a constant such that you cannot approximate the problem within this constant. So there is no approximation scheme in polynomial time. Some other results on the positive side. For all the other cases, so path or subdivision of the claw, there is a QP-TAS. QP-TAS is an approximation scheme running in quasi-polynomial time, n to the power of polylog n. It is a recent result, so that of this year. Other positive result, it is polynomial time solvable in P5 and also in P6 free graphs. It is also a recent result. And it is also polynomial in a fork free graph. The fork is the claw with one subdivided edge. And lastly, still by Ramsey's theorem, there is an approximation algorithm in KR free graphs with approximation ratio n to the power of 1 over r minus 1. So for instance, in triangle free graph, there is a square root of an approximation. So the main motivation of our work is that finding any general n to the power of something non-trivial approximation algorithm would be nice, and by general I mean something that would encompass several graphs H, and the natural candidates are graphs satisfying the Erde-Hajnal property. So suppose that you have a graph H satisfying the Erde-Hajnal property. So you always have either a clique or an independent set of size n to the power of some constant epsilon. Then consider the following algorithm. So either there is a clique, either there is an independent set S in your graph. In that case, you return this solution, or it returns a clique. In that case, you remove this clique, you put it apart, and you remove it from the graph, and you continue the same algorithm until we have enough vertices, and enough means at least n to the power of 1 minus epsilon h vertices, the epsilon being the epsilon h of the Erde-Hajnal property. So let's analyze this algorithm. So we might have several cliques and then the remaining vertices. So either we return an independent set at some point, maybe at the very beginning or maybe after some clicks. But if we return the independent set, then since the number of remaining vertices is large enough, we can say that the solution by Erde-Hajnal is also large enough of size n to the power of epsilon minus epsilon square. And if we never return an independent set, then we will end up with too few vertices to continue, so namely smaller than n to the power of 1 minus epsilon. But in that case, by the same argument as previously, we can see that every click is of size larger than n to the power of epsilon minus epsilon square, which means that there cannot be that many clicks, so q is smaller than this. And if q is smaller than this, then we cannot construct an independent set in the graph which is very large. So namely we can pick at most one vertex per click and maybe all the remaining vertices. And in total this is always smaller than n to the power of 1 minus epsilon square plus delta for every delta, assuming n is large. So if we sum up, in the first case we output a solution of this size, and in the second case we have the certificate that the size of the largest independent set in G is smaller than this. And in that case we'll just output one singleton as the solution. And you can check that in both cases the ratio between the size of an optimal solution and the size of the output solution is always smaller than this. So the output solution is always an approximated solution with this approximation ratio. So it answers positively the previous question. We have a general result saying that for every graph H we satisfy the Erde-Hajnal property, then we can approximate maximum independent set within a ratio of n to the power of 1 minus delta H for some constant delta H depending on the constant of Erde-Hajnal. So there's a little trick. It has to satisfy namely the constructive Erde-Hajnal property, because we not only need to know the existence of a homogeneous set, but we need an algorithm which outputs either a click or an independent set. So we call it the constructive Erde-Hajnal property. But for all graphs H satisfying the Erde-Hajnal property, we also have an algorithm finding the homogeneous set. So this is roughly the same. So this result led us to define the following notion. A graph H has the improved approximation property if the maximum independent set problem admits an n to the power of 1 minus delta H approximation algorithm for some non-trivial delta. So this is kind of the same flavor as the Erde-Hajnal. This is why we called it an algorithmic weakening of Erde-Hajnal. So we have the same conjecture as Erde-Hajnal. Any graph H satisfies the improved approximation property. So we have just seen that having the constructive Erde-Hajnal implies the improved approximation property. But there are also graphs which satisfy the improved approximation property, but are still open for Erde-Hajnal. And for instance, P5 and P6. P5 is still open for Erde-Hajnal, so P6 is also open for Erde-Hajnal. But P6 free graphs, in P6 free graphs, maximum independent set is polynomial time solvable, so the approximation ratio is even 1, right? And third point, we were able to prove that the improved approximation property is also preserved by the substitution operation. So the operation which works for Erde-Hajnal also works for our new property. So let me say a few words about this result. So let's try to give some idea about this. The improved approximation property is preserved by the substitution operation. So to simplify the task, let us suppose that we substitute H with H itself at some vertex V. So we pick one vertex V in H, and we replace this vertex by H itself. Okay, and we assume that H satisfies the improved approximation property. So there is an n to the power of 1 minus delta approximation algorithm in H-free graph. So we assume that we have a graph G with no induced H star being the substitution of H by H. So there is no H star, but there might be some H somewhere, okay? There might be several copies of H in my graph G. And actually we will count this number of copies. So we can easily count it in polynomial time because H is fixed, okay? So we can run through all possible subset of vertices of size of H. So two cases. First, there is almost no copy of H in G. I won't get into the detail of what almost no copy means, but this is just to get the idea. If there's almost no copy of H in X, what we do is that you take a random subset of vertices of the right size, and with high probability G of X is H-free. And if it's H-free, since H satisfies the improved approximation property, we run the approximation algorithm of this subgraph induced by X, and we get a solution. Second case, there are many copies of H, many copies of H. In that case, you pick a set of vertices that we called H minus, which induce H minus the vertex V we are using for the substitution. Okay, so this is H minus the vertex V. And we consider all the vertices X with the right neighborhood with respect to H minus, such that adding any vertex from X to this set creates H star. Sorry, the star is missing here. Okay, so this is exactly sorry. This is H. So adding any vertex from X creates H. Okay. So obviously G of X is H-free because having H somewhere here would create H star. And if there are many copies of H in X, if there are many copies of H in G, then there must exist H minus such that the set of candidates X is large. And in that case, we run the approximation algorithm on G of X, and we get a solution S. So in both cases, we are able to identify a set X, a large set X, which is H-free, in which subset we run the approximation algorithm. So if we output a solution of the right size, we are done for some constant delta. Otherwise, we delete the set X and we continue. Same thing as the previous algorithm. And intuitively, the size of the maximum independent set in G of X is small because the solution was not large enough, and the solution is an approximated solution. So we get a set X where alpha is small, and we put it apart, and at the end, if not enough vertices remain, then the collection of X certifies that the alpha of G was small at the beginning. So same idea of the previous algorithm. In that case, we output an arbitrary vertex of the solution. Okay, so we have seen that constructed Erde-Hajnal implies the improved approximation property, but there are also some graphs such as P5 and P6 which satisfy the improved approximation property but are still open for Erde-Hajnal, and we have seen that the improved approximation property is preserved by the substitution operation. So the interesting fact about our conjecture is that there exists infinitely many graphs H by combining, for instance, P5, P6 and the substitution operation. So many graphs H satisfying the improved approximation property for which the Erde-Hajnal conjecture is still open. So our new conjecture is strictly simpler. So our conjecture is about finding some approximation algorithm with approximation ratio n to the power of 1 minus delta H. So let's talk about some value of delta for known graph classes. For triangle-free graph, we have a square root of n approximation, so delta equals 1/2. The clique of size R the delta is r minus 2 over r minus 1. Okay. P6 free graph, of course, delta equals 1 because this is a 1 approximation. The constant delta we obtain for bool free by using the proof for Erde-Hajnal in bool free is 3 over 16. So we have several values of this delta, and natural question is, for a given h, what is the best constant delta we can hope for? And also, can we prove lower bounds for some graph h? Maybe some approximability ratio is hopeless to obtain, because in the approximation, in the approximability area, we have some tools in order to prove approximation lower bounds. So maybe we can prove some lower bounds on this constant delta. And this is actually what we did. And our main result concerned graphs with high girth. And for instance, for triangle free graphs, we were able to so there's an easy, as I said, square root of an approximation algorithm. So either there is a square root of n degree vertex, or you can greedily construct a solution of size square root of n. And this can be generalized to graphs with girth gamma to n to the power of 2 over gamma minus 1 approximation for graph with girth gamma, and even for graph with odd girth gamma. So the question is, can we beat the constant 1/2 for triangle free and this constant for large girth? And the answer is yes. We were able to prove that maximum independence set cannot be approximated within a ratio of n to the power of 1/4 minus epsilon in triangle free graphs. And it can be generalized to this ratio for graphs with girth gamma, 1 over 2 times gamma minus 1. So this is not, so the results are not tight, but they are almost tight. So the gap is only of 1/2 of 1/4 in the triangle free case, for instance. So they are random. We use randomized reduction, so which means that the hypothesis we use here is NP not included in BPP, which is the randomized version of P equals NP, more or less. So let's have a look about this result for graphs with high girth. So the idea is to define a reduction from the gap version of maximum independence set, because maximum independence set cannot be approximated within n to the power of 1 minus epsilon. So roughly we can start from an arbitrary large gap, and we have to map the no instances, so instances with no independent set of size n to the power of epsilon, to instances with girth gamma with no independent set of size n to the power of something plus epsilon, and the yes instances must be mapped to yes instances. And we have to transform an arbitrary general graph into a general graph H into a graph G with girth gamma. This is the difficult task. So the idea is the following. The input is a graph H on big N vertices. First step is to replace every vertex of our graph by an independent set of the appropriate size. I won't get into the details, but it's the size big N of to the power of some function of gamma. And we replace each edge by a complete bipart diagram. The second step is to consider another graph, a host graph, on the same set of vertices as the new graph here we obtain. Okay, we consider a host graph in blue, F, on the same set of vertices, with a large girth gamma, and with the following property: it cannot contain subsets A, B of vertices, each of size n to the power of delta, such that there is no edge at all between A and B. Delta is a constant that we will talk about later. So we consider this roughly this new set of edges, and basically we take the intersection of these two edge sets. So it will remove some edges from the previous graph. We obtain a new graph which has the following property. Obviously it has girth gamma because f has girth gamma, and because of this property, if you take two sufficiently large subsets in two adjacent bags, then you must induce an edge, which means that you cannot really cheat when you get an independent set in your obtained graph. It must somehow implies a large independent set in the previous graph H. So the gap, the gap is not degraded too much. So this is just the idea. So some question about this host graph. What is this host graph? The main ingredient is graph with large girths and no subsets AB of large size, such that there is no edge at all. So roughly complement of complete bipartite graphs. How do we construct it? Then we can construct it by using the already known constructions of graphs with large girth and small independence number, except that we have to adapt. Instead of having no large independent set, we want no large complement of bipartite graph, roughly speaking. So basically considering the triangle removal process and then analyzing the triangle removal process for triangle-free graphs allows to obtain graph with this property. So there are many randomized reduction. This is why we only get NP not included in BPP for the best inapproximability bounds. So what we have so far is this inapproximability ratio for graph on girth gamma, and in triangle-free graphs we get n to the power of 1/4 minus epsilon. So there is still a gap for the triangle-free case, which is quite interesting. What is the right answer? So as a conclusion, I would say that the main contribution of the paper is the conjecture we introduce, so the algorithmic weakening of the Erde-Hajnal conjecture, which is that for every graph H, the maximum independent set problem can be n to the power of 1 minus delta H approximated in H-free graphs for some constant delta H positive. I will simply mention two open questions. So we have seen that this is strictly simpler than the constructive Erdos-Hajnal conjecture. So the natural question is, what about graphs which are notoriously open for Erdos-Hajnal conjecture that I didn't mention previously, so not the P5 and P6 case. So the first candidate is, what about C5? So C5 is still open for Erde-Hajnal, and it is still actually open for our conjecture. We could not find an approximation algorithm with n to the power of anything non-trivial. So by the way, we are talking about C5 free graph, but the case of C5 free graph, but the case of C4 free graph is quite different, because so I didn't present it here, but using the classical local search algorithm, you can easily prove that C4 free graphs admit an easy square root of n approximation algorithm. And the reason it works for C4 is because C4 is a complete bipartite graph. So actually, our conjecture is also true for every complete bipartite graph H, so in particular C4. But still open for C5. So I think that having an approximation algorithm for C5 free graphs might be easier than Erde-Hajnal, so it would be an interesting first step for proving Erde-Hajnal. And the second question is a natural question, what about closing gaps, approximation gaps, finding the best delta H for a graph H? And the case of triangle-free graphs is quite interesting. We still don't know whether there is an n to the power of 1/4 approximation algorithm. It it would be quite surprising, but on the other hand, we have the feeling that our lower bound framework cannot be used to prove square root of n in approximability results. So either we have to design a new we have to use new IDs for the inapproximability, or maybe there is such an approximation algorithm for triangle-free graphs. That would be quite surprising. And that's all. Thank you for your attention.